All right, today we're diving deep into one of the most absolutely mind-bending questions in all of physics. We're going to follow the strange, wonderful, and sometimes downright bizarre mathematics of Albert Einstein's theories all the way to their most extreme reality-warping conclusions.
So let's just jump right in with the big one, the question that gets everyone's imagination fired up. What would actually happen if you fell into a black hole? It sounds like it should be a simple question, right? But as you're about to see, the answer is anything but.
Because here's the crazy part. According to general relativity, the answer depends entirely on your point of view. Seriously, what you experience and what someone watching you from a safe distance experiences are two completely different, yet equally valid realities. And that's where our whole journey kicks off.
This brings us to the first great mystery we have to tackle, what's known as the frozen horizon paradox. So, imagine you're floating in space, watching a friend's spaceship head towards a black hole. What you would see from your safe spot, well, it's just plain weird.
From your vantage point, that spaceship seems to slow down as it gets closer and closer to the black hole's edge, the event horizon. It's like time itself is stretching out for the ship. And then, right at the very edge, it looks like it just freezes. It stops. The light from it gets redder and dimmer until it just fades away into nothing. You would literally never, ever see it cross. This apparent impossibility puzzled scientists for decades, Einstein included.
Okay, so to even begin to wrap our heads around this, we actually have to rewind a bit. We need to look at the problem Einstein was trying to solve in the first place. You see, he was wrestling with a huge, fundamental issue in Isaac Newton's legendary theory of gravity.
Okay, so here's the crucial difference. Newton thought of gravity as some kind of mysterious force, acting instantly across empty space. Einstein came along and offered a much more elegant and frankly beautiful solution. He said there is no force. Instead, massive objects like our sun literally bend and curve the very fabric of space-time around them. Planets aren't being pulled by the sun. They're just following the straightest possible path through that curved space.
And you know what? Even Newton himself was deeply bothered by his own idea of action at a distance. He actually called it a great absurdity. It just goes to show you that even the absolute giants of science can be stumped by the weirdness of their own discoveries.
And that is the very heart of general relativity. Gravity isn't a force, it's geometry. It's as simple and as complicated as this. Mass and energy tell space-time how to curve, and in return, the curve of space-time tells matter how to move.
So, right after Einstein published his incredibly complex equations in 1915, he couldn't actually find a perfect, exact solution for them himself. But then this astrophysicist, Karl Schwarzschild, while serving on the Russian front during World War I, of all places, he found one. And lurking deep inside his solution were, well, mathematical monsters.
You can really see on this timeline how this wild idea started to take hold. I mean, back in 1916, Schwarzschild's math predicted a singularity, a point where everything breaks down into infinity. For years, pretty much every physicist just dismissed it as a quirk in the math, something not real. But then the work of Chandrasekhar and later Oppenheimer proved that for the biggest stars, collapse into this state wasn't just possible, it was inevitable. The monsters in the math were real.
So Schwarzschild's solution basically had these two, well, let's call them problem spots, where the math just went completely haywire. The first was right at the center, r equals 0, where density and gravity became infinite. The second was at a very specific distance from that center, the Schwarzschild radius, which we now know as the event horizon, the point of no return.
Okay, so how does any of this help us with our frozen horizon paradox? How can the spaceship both fall in and freeze at the edge? Well, the solution lies in a really simple but powerful analogy. Our mathematical descriptions of spacetime, they're just maps, and every map has its limits.
Think of it this way. A coordinate system is just a map we draw on top of spacetime to help us find our way around. Schwarzschild's system is a great map if you're an observer far away from the black hole. But once you get close to the event horizon, that map starts to get really, really distorted. It's like trying to perfectly flatten an orange peel. It's just not going to work.
You know this from looking at any map of the Earth, right? Take the common Mercator map. It's awesome for navigation because it keeps angles true, but it makes Greenland look as big as Africa, when in reality, Africa's 14 times larger. Then you have another map, the Gall-Peters, which gets the sizes right but totally warps the shapes of the continents. Neither map is wrong. They're just different tools with different distortions.
And that's exactly what's happening with the black hole. That image of a spaceship frozen at the horizon, that's just a feature of the Schwarzschild map. It's what space-time looks like from the coordinate system of a faraway observer. The event horizon is simply the place where that particular map gets completely stretched out and distorted, just like the North Pole on a Mercator map.
So here it is, the big reveal. If you choose a different map, a coordinate system that actually travels with the falling spaceship, that crazy distortion at the horizon completely disappears. From the traveler's point of view, they sail right across the event horizon, no problem. And from the distant observer's point of view, they really do see the ship freeze forever. Both views are correct. It's relativity in its purest and strangest form.
But wait, it gets even weirder. Once physicists realized they could just switch maps, they set out to create the most complete, maximally extended map of a black hole spacetime possible. And what that map revealed, when you just followed the math where it led, well, it was stranger than anyone could have possibly imagined.
This complete map, wow, it doesn't just predict a black hole, it also predicts its time-reverse twin, a white hole, an object that nothing can ever enter and from which everything is violently spewed out. The math also predicts a second parallel universe connected to our own through something called an Einstein-Rosenberg, what we'd call a wormhole. This isn't science fiction, it falls directly, logically, out of Einstein's equations.
But it gets even wilder, because, real things in the universe spin, and a spinning black hole is way more complex. Just look at this table. For a rotating black hole, the singularity isn't a single point anymore. It's a ring. And that is a huge deal because it means the path to that singularity is no longer inevitable. You can actually avoid it.
And this leads to a conclusion that is pure sci-fi. The math suggests that you could, in theory, pilot a spaceship straight through the center of that ring singularity and come out the other side. Not crushed into oblivion, but into a brand new universe.
Okay. Wow. Let's just take a breath for a second here. Parallel universes, white holes, gateways through singularities, it's a lot to take in. So we have to ask the big question. Is any of this stuff actually real, or is it just a beautiful fantasy that exists only in the mathematics?
Well, for now, the consensus among most physicists is probably not, and here's why. First, these solutions describe eternal black holes that have existed forever, not the ones in our universe that form from collapsing stars. Second, that inner gateway in a rotating black hole is thought to be incredibly unstable. The tiniest bit of energy falling in would probably cause it to collapse. And finally, to make a stable wormhole you could actually travel through, you need exotic matter with negative energy, which is something we've never seen and that seems to violate the laws of physics.
But before we dismiss it all as fantasy, let's remember this quote from the famous astronomer Arthur Eddington. He was talking about the very idea of a star collapsing into a black hole in the first place, and he called it absurd. He was absolutely sure nature would find a way to stop it, and of course, he was completely wrong.
Which leaves us with a final, really tantalizing thought. The idea of black holes was once considered a mathematical absurdity. Today, we have actual pictures of them. So, what seemingly impossible math that we're grappling with today might just turn out to be the accepted reality of tomorrow. Thanks for joining this explainer.